Okay, so we've got a multivariable calculus question here. We're going to solve the Euler Lagrange equation for this functional here, which is integral from 0 to 1 with regards to x, 2y squared plus 4xy plus 2y prime squared. So we've got three variables as such in here. So our functional here is made up of x, our y, and our y prime, where f equals 2y squared plus 4xy plus 2y prime squared. Okay, so solve the Euler Lagrange equation. Well, the Euler Lagrange equation we know is like this. So it's the derivative of the partial of f, which is our functional here inside the integral. So with regards to y prime, and then we subtract the partial of f with regards to y. So these are y prime and our y's, and we set this to equal 0. So we try and solve this. This is what we're looking for. Well, we can do these parts of the left hand side of the equation here quite straightforward. So the partial of f with regards to y prime. So we look for all the y prime terms, and we've got a 2y prime squared. None of these concerned y prime, so they're all counting as constants as far as y prime is concerned. So these are eliminated. So the derivative of 2y prime squared would just give us 4y prime. So partial derivative of with regards to y prime, that's just going to give us 4y prime. And then the partial with regards to y, I'm going to have two terms here because we've got two y terms. So 2y squared, that's just 4y, just same as single variable calculus. And 4xy, well, the y will reduce to 1, and then we're left with the constant, which is 4x as far as y is concerned. And then that is set to 0. Okay, so derivative 4y prime, well, that's just 4y double prime minus 4y plus 4x equals 0. Okay, well, we've got 4 as a coefficient of all the terms, so just divide everything by 4, and obviously with the 0 we're still left with 0. So we can simplify this off to y double prime minus y, and then let's distribute the minus here to get rid of this bracket, so I prefer to remove that. So that gives us then minus x equals 0. Okay, so we've got our Euler Lagrange equation, which we now need to try and solve. So let's just write this up here now, y double prime minus y, and then bring the x on the other side, because we're now going to go into partial differentiation. So we're going to try and solve with regards to that. Sorry, it's not 0, it is x. So if I bring this x over the other side, I get positive x. Okay, right, let's take this off the board and let's try and solve this partial derivative here. So what we will have y of x as our answer, and that will be made up of two parts. It will be made up of our homogeneous version of yh of x, so we need our building blocks for that. So yh of x, not yx of x. Yh of x, just h subscript for homogeneous, and a particular solution which will involve using the x. So yp of x. Now our homogeneous solution we will set to 0. So let's have a look at that. So we want y double prime minus y. So it's set into x, we will set it to 0 instead. And at this stage we need to decide how we're going to make our answer built up of certain functions. So we don't know what that function is. So the one we can use is our y of x, as in our homogeneous, will be made up of e to the lambda x in some sort of form. Now lambda is a constant which we don't know. So if this is going to be the form of our function, what we do is we take the second derivative of this, subtract it and let it equal 0 and see where we get to. So this is second derivative, so dx squared of e to the lambda x, and then subtract our e to the lambda x and let that equal 0. Okay, let's take the second derivative of this function here. So we're taking it with regards to x, so the lambda is only a constant. So the lambda will come out first for the first derivative, so lambda e to the lambda x. That's our first derivative. And our second derivative, the lambda again still a constant, so bring the lambda out front. So then we're left with lambda squared e to the lambda x. So that's our second derivative. So that's our first. We just take that one off the board to avoid any confusion. And then subtract this, nothing to do there, so just write it in. And then set that to equal 0. Okay, how can we solve for lambda here? Well, let's factor out the e to the lambda x. So we've got a lambda squared. That takes care of the first part. Then e to the lambda x, so here we just subtract 1 and of course set it to 0. Okay, e to the lambda x, when is that ever 0? So exponential function is never 0 regardless of x or lambda, so this is never 0. So the only way this could be 0 is if this here is 0. So let's just bring this down here now. Lambda squared minus 1 equals 0. Then our lambda squared equals 1. So our lambda equals plus or minus 1. So that's pretty straightforward. So let's write our homogeneous solution up on the board now. This is our building blocks for our answer. So then what we do is now we've got two versions of lambda. We've got a plus 1 and a minus 1. So we've got e to the plus x and e to the minus x. We'll also need a constant in front of here as well, which we don't know. So I'm going to write that now as a, e. So put the positive x in first, so positive lambda, so positive 1 lambda will just give us x. And then we're going to add b, which is our second arbitrary constant. Then e to the negative x. So that takes care of our negative lambda. Okay, that's our homogeneous part of the building blocks. So now yp of x. Let's have a look at that. So we take this off the board. So I'm going to just take that off. Just take this 0 off. Because now the particular solution, we want to set it to equal x. Now x here is a linear function. So our building blocks for the particular solution, we're going to have a linear function. So we need two new constants as well. We used a and b. So next one in the line we'll use c and d. But as it's a linear function, we'll have d as our gradient for x and c could just be our intersection point. Okay, so now y double prime minus y equals x, and this is our building blocks for our y. So now we need the second derivative of this, just as we did with the homogeneous solution. So c plus dx minus our y, which is c plus dx. This time we're going to set it to x, we won't set it to 0. Okay. Well, the second derivative of this is going to disappear to 0 because first derivative of c, that will become 0, and then the dx will just leave us with d, and then derivative of this, they will both become 0. So I'm just going to exchange that for a 0. That's pretty straightforward. And then minus c plus dx, nothing to do there. Set that equal to x. Okay, now let's see if we can find our constants here, c and d. So we've got minus c, distribute the minus, that's a minus dx, that equals x. Alright, so there's no constant here, so I'll just write a plus 0 so you can easily see what's going on here. So our only constant here is c, which is on its own. So if minus c gives us our 0, c is also 0. So that's straightforward. So now we're left with minus dx equals x. Now what does d have to be? So this side equals x. Well, d has to be minus 1. So that's our thing here. So then that just leaves us with x equals x, which is what we want. That's obviously true. So now we can write our particular solution for x. So that is going to be minus dx. So our d is minus 1. So c plus dx, c is 0. So I'm going to write this c plus minus 1 x, which equals minus x. So yp of x equals minus x. So that's what we got there. So now we can write in there now. Oh, I've just taken that bit off the board. Let's keep that on. We can now ready to write our solution for y of x. So our homogeneous, which is this one here, and then our particular solution, which is just minus x. And then that is our solution. So our question, y of x equals a e to the x plus b e to the minus x minus x. A and b are constants. Okay.